only have to go up to halfway, because otherwise you'd be adding 1 or 2 would have already. Yes. So
All right, how's it going? Good stuff. Happy Valentine's Day. Yay. If you're into that. So, any questions? Which chapter are we in?
5, number 7 is prove that the square of any integer is of the form 3k or 3k plus 1.
All right, so prove that the square of any integer is of the form 3k or 3k plus 1. Could be a what? Could be a modular question. How will we phrase this in terms of modular things? That's the right direction, though. So let's work mod 3. So what is this saying about n squared mod 3? It's congruent to either 0 or 1. So prove n squared is congruent to 0 or n squared is congruent to 1 mod 3. Bless you. So here's the deal, right? If we wanted to prove this for any integer, its square is congruent to 0 or 1, right? We could take every integer and square it and see what it's congruent to modulo 3. So 0 squared is 0, that works. 1 squared is 1, that works. 2 squared is 4, that works. 3 squared is 9, that works, and so on and so forth. But we don't have enough paper to write that out for every integer, because there's an infinite number of integers. But because we know that we can do most arithmetic modulo something, right? We can multiply, we can add, we can subtract. We can't divide in general. But if A is congruent to B, we can multiply both sides by something. We can add something to both sides, and we still have that congruence, right? So because we can do that, and we know that every number is congruent to either 0, 1, or 2 mod 3, we can make a statement about every integer that's congruent to, say, 1 mod 3 by doing arithmetic modulo 3. So this basically gives us a set of cases, because any integer that we can imagine is congruent to either 0, 1, or 2 mod 3. So let's just do 3 cases. So case 0, n could be congruent to 0. Case 1, n is congruent to 1. Case 3, n is congruent to 2. Doesn't matter what integer we pick, one of these 3 situations must be true. All right, so if we can show that for each of these cases, n squared is congruent to either 0 or 1, we should be done. So if n is congruent to 0, do we know what n squared is congruent to? It's 0, right? It's 0 squared, which is just 0. If n is congruent to 1, n squared is congruent to 1 squared, which is 1. And if n is congruent to 2, n squared is congruent to 2 squared, which is 4, which is congruent to 1 modulo 3. And so in the only 3 possible cases, we've shown that either n squared is congruent to 0 or n squared is congruent to 1, which is exactly what we were asked to show. Exactly. If it's mod n, you're going to have basically n cases from 0 up through n minus 1.
Can you take mod 3k, or is that not going to work?
Mod 3k?
Yeah.
What is k?
I just said it was any integer.
Well, that's working over an infinite range of moduli then.
Okay.
Right? So you could be working mod 3, mod 6, mod 9, and so on. And that's probably going to take you in a different direction. Bless you. So lots of problems that ask us to make a statement about all integers, particularly if that statement involves division or remainders, right? Think about trying to prove it in particular cases and see if you can get an answer that way. All right, other questions? So what about problem 8? I don't think I assigned that, right? So use problem 7 to prove 3m squared minus 1 is not a perfect square for any integer m. So prove 3m squared minus 1 is never a perfect square. So what could we do to maybe get here? When you're asked to prove that something's not the case, first thing you might think, or one of the first things you should probably think, is proof by contradiction. Because we don't really have a lot of machinery that lets us systematically go through and come down with a conclusion that, you know, this never happens. We can start with something that's true and come down and say, you know, this is true and this is true and this is true. But we can't really start with something that's false and then come up with things that are false. So when you're asked to show that something is false, think proof by contradiction. So suppose (3m squared minus 1 equals k squared), where k is an integer. And it says to use exercise 7, which we just did. So exercise 7 said that k squared is congruent to 0 or 1 mod 3 for all k contained in Z. So in particular, this must be true for this particular k that we're claiming 3m squared minus 1 is equal to. So there's two possibilities. Well, how do we want to do this? So k squared equals 3m squared minus 1. Well, exercise 7 tells us something about k squared mod 3. So let's look at this equality mod 3. So what is k squared congruent to mod 3 given this statement? 2, or -1. It's 1 less than a multiple of 3. Right? 3n squared is congruent to 0, so 3n squared minus 1 is congruent to -1. And -1, if we want to stick to numbers between 0 and 2, -1 is congruent to 2. So if this statement is true, then k squared is congruent to 2 mod 3. But from exercise 7, we know that k squared is always congruent to either 0 or 1. So this is a contradiction. And therefore, it's not possible that 3m squared minus 1 is k squared. So 3m squared minus 1 is not a perfect square. Kind of makes sense? These are definitely solidly in the realm of puzzles, right? You have different things you can do, and you're basically trying to find some way to look at a problem that brings you to the solution. But it's not an algorithm like KVL, KCL, where you do this, do this, do this, and there's your answer, right? It takes some trial and error, but the more you play with it, the more proficient you become at using these different tools or tricks.
Can you do 5.2, number 6?
We can look at it.
Like, I know why, like, how to go about proving it, but I don't know what I wrote down is, I don't know if I wrote it down so it makes sense.
So prove power multiples of 4. Yeah. So prove that that set contains a multiple of 5. So what was your idea?
Well, 5 equals 4 plus 1.
Mm-hmm.
And all the elements of that set are n plus 4 times some integer.
Okay.
Where including 0.
Okay.
On that.
So there's our 5 numbers. So I like the start. Do we believe this? So what happens if we pick some numbers, n equals 7? So what do we get? We get 7, we get 11, we get 15, we get 19, and we get 23. And sure enough, there's a multiple of 5 in there. If we pick 8, we get 12, 16, 20, and 24, and there's a multiple of 5. If we pick 6, there's a multiple of 5. Same thing with 9. And if we pick n equals to 5 or 10, it's certainly going to contain a multiple of 5 because n itself is a multiple of 5. So yeah, there's something about this. There's something about going up by 4s. How about this? So each time we go up by 4, we go up by 5 and we take away 1. The next time we'll go up by 10 but take away 2. The next one will go up by 15 but take away 3, and so on. So the intuition is there. The way we can add rigor to that is with modular arithmetic, right? Modular arithmetic is a way to capture things that we sort of see about numbers, about successions of 1 that eventually add up to 5 or things like that. So think about this. We're looking for a multiple of 5. Let's just go into a modulo 5 universe. Everything is either 0, 1, 2, 3, or 4, congruent to 0, 1, 2, 3, or 4 modulo 5. And we can write a set of 5 numbers and we can say prove either n is congruent to 0, n plus 4 is congruent to 0, n plus 8 is congruent to 0, n plus 12 is congruent to 0, or n plus 16 is congruent to 0 modulo 5. And this is for any n. So we can rephrase this problem for any integer n and prove that it's either n is congruent to 0, or n plus 4 is, or n plus 8 is, and so on. And again, we can break it into 5 cases. N itself could be congruent to 0, 1, 2, 3, or 4. Well, if n is congruent to 0, we're done because n is congruent to 0. If n is congruent to 1, n plus 4 is 5, which is congruent to 0. And so we're done, and so on. If n is congruent to 2, n plus 8 is 10, which is congruent to 0. If n is congruent to 3, n plus 12 is 15. And if n is congruent to 4, n plus 16 is 20, which is congruent to 0. And so in any of these 5 possible cases, we've proven that at least one of these 5 statements is true, which means that one of these expressions is divisible by 5. And that's all you got to do to prove this. And it's doing this under the hood, right? It's using this idea that when we add 4, we're adding 1 less than a multiple of 5. So if we were 3 shy of being a multiple of 5, after we add 4 3 times, we'll have taken away 3 from a multiple of 5, right? And that'll bring us back to a multiple of 5. That's the idea of what's going on. But even without that intuition, right, you see something about multiples or divisibility or remainders, think modulo whatever it is that you're being asked to divide by or take a multiple of, and then think about cases. And sometimes you do one of these proofs and you manage to prove it and it leaves you with like 0 insight into what's actually happening, which is kind of cool in its own way because it means you're really like using some machinery that's telling you something that your intuition isn't, right? That's where math gets to be really cool, is when it can surprise you like that. All right, other questions? All right, well, let's keep talking about primes. If we think about numbers modulo 4, and you have an odd number, can we say what n is congruent to modulo 4? Can we say something about what n is congruent to modulo 4? Could be congruent to 3. For example, 3 is an odd number, and 3 is congruent to 3. Could it be congruent to something else? What? Could be congruent to 1, right? 1's an odd number, and 1's congruent to 1. Could it be congruent to 0? Can a multiple of 4 ever be odd? Right? 4 itself is even, and an even number multiplied by anything is even. Right? If you want to prove that, 4 is congruent to 0 mod 2, and so 4 times anything is congruent to 0 mod 2. So 4 times any number is going to be even. So n is never congruent to 0. Could n be congruent to 2? Right? If it's congruent to 2, it's 2 more than a multiple of 4. Since a multiple of 4 is even, something twice more than an even number is also going to be even. So n cannot be congruent to 2. So any odd number is necessarily congruent to either 1 or 3 modulo 4. And that doesn't always work. For example, mod 3, an odd number could be congruent to 0, like 3. Could be congruent to 1, like 1. Or it could be congruent to 2, like 5. So modulo 3, odd numbers could be congruent to either 0, 1, or 2. But modulo 4, an odd number has to be congruent to either 1 or 3. Okay, that's useful in one of the homework questions. So every odd number, let's say any odd number, can be written in the following form: 4 times k plus 1, or 4 times k plus 3, where k is an integer. Since this is true for any odd number, it's true for any odd prime in particular, because odd primes are odd numbers. So any odd prime can be written as 4k plus 1 or 4k plus 3 for some k being an integer. And so we can ask, well, since any prime number can be written in one of these forms, how many primes can be written like this, and how many primes can be written like that? We know there's an infinite number of odd primes, but is it possible that there's only a finite number in this form, and all the other primes are in this form, or vice versa? Or is there an infinite number of primes in each of these forms? And it turns out, in general, there are an infinite number of primes of each form. Not obvious how to prove that, but it turns out to be true. So there's an unlimited number of primes that are congruent to 1 mod 4, and there's an unlimited number of primes congruent to 3 mod 4. Viewed differently, if we were to write a sequence, 1, 5, 9, 13, 17, 21, 25, that sequence is going to contain an infinite number of primes. And if we start from 3 and we write 3, 7, 11, 15, 19, 23, that sequence will contain an infinite number of primes. And that's provable. But there's an even more general result. So in general, if A and B are relatively prime, so there's no common divisor between A and B, then the sequence consisting of all A times K plus B, where K is an integer, also contains an infinite number of primes. So for example, I could start with 8, and I could count up by 5s. So I could have 8, 13, 18, 23, 28, 33, 38, 43. That's going to have an infinite number of primes. So that's kind of a cool result. That kind of tells you that there's lots of primes, and these primes are kind of scattered all over the place. Enough that we'll hit an infinite number of them with any sequence that we choose, except the silly sequences where A and B have a common factor. For example, if A equals 8 and B equals 4, I'm not going to find any primes. So I'm going to have 8 and 12 and 16 and 20 and 24 and so on. And I'm not going to have any primes because whatever divides A and B is going to divide everything in this series. But other than that silly case, right, any sequence of this form gives us an infinite number of primes. So that's kind of cool, maybe. All right, so we talked about greatest common factors or greatest common divisor. So greatest common divisor of two numbers, I don't know. Let's do 101 and 37. So we had this Euclidean algorithm. How many people have done this yet on the homework? Ooh, lots of emails coming, I suspect. All right, so 101 equals, so how many times does 37 go in? I think it's twice. 2 times 37 plus 74, 27 maybe? You're going to have to check my math for me. 37, 74, 94, I think that's right. And so bring this over. 37 equals 1 times 27 plus 10. Is it 26? 27? Okay. So bring these over. 27 equals 2 times 10 plus 7. Bring these over. 10 equals 1 times 7 plus 3. Bring those over. 7 equals 2 times 3 plus 1. And bring those over. 3 equals 3 times 1 plus 0. And once you get down to a 0, this is your GCD. So the greatest common divisor of 101 and 37 is 1. Which makes sense because they're both prime numbers. There can't be anything that divides them both except for 1. right? The only divisor of 37 is 1 or 37. The only divisor of 101 is 1 or 101. So 1's certainly going to be the greatest common divisor. Well, there's a cool theorem called Bezout's theorem. It's fun to say. And it says the GCD of two numbers, a and b, can be written as a times some integer plus b times some integer. So for some x and y contained in z. Did I mess up? So Bezout's theorem says if you have the GCD of two numbers, you can write that greatest common divisor as some linear combination of those two numbers. Okay, the first number multiplied by an integer plus the second number multiplied by an integer. Which tells us in particular for numbers that are relatively prime, there exists an x and a y such that 101 times x plus 37 times y is equal to their GCD 1. And this is going to be useful when we do crypto systems. But for now, we can accept Bezout's theorem that there is a way to write a combination of those two numbers that will get us to 1. But it's pretty easy to do an algorithm to find these values x and y. Basically, once you've applied the Euclidean algorithm, you can work in reverse and fill in. So remember, the reason the Euclidean algorithm works is because the GCD of 101 and 37 will be the same as the GCD of 37 and 27, which is the same as the GCD of 27 and 10 and 7 and 7 and 3 and 3 and 1. Right, because if you do the modular arithmetic, you end up with divisors carrying through. So what we can do is we can take this GCD 1 and we can write this as 7 minus 2 times 3, just sort of reversing this equation here. Just carrying the 2 times 3 on the other side. So that's just 1 equals 7 minus 6. No surprise there. But this 3 we can write in terms of 10 and 7. So 3 is equal to 10 minus 1 times 7. And if we plug that in, now we've got 1 equals 7 minus 10 plus 7. So it's, I'm making a mistake here. 7 minus 2 times 10 minus 1 times 7. So that's 7 plus 7 is 7 plus 2 times 7, that's 3 times 7, and then minus 2 times 10. So we've written 1 as a linear combination of our 7 and our 10. And now we can take this 7 and we can write this as 27 minus 2 times 10. And if we plug that in, we'll get 1 as a linear combination of 27 and 10. And if we plug in this expression for 10, we'll get 1 as a linear combination of 27 and 37. And if we plug this in, we'll get 1 as a linear combination of 37 and 101. So it's some legwork, but it's very mechanical, and you work backwards and basically can get to this linear combination. So let's do that with something simpler. So GCD of 31 and 17 should be equal to 1. So let's see if this works. 31 equals 1 times 17 plus 14. 17 equals 1 times 14 plus 3. 14 equals 4 times 3 plus 2. 3 equals 1 times 2 plus 1. 2 equals 2 times 1 plus 0. So there's your GCD. I tried this morning. I couldn't get a complex example to work out. They all ended up being like 2 lines long. So now I can't get a simple one. That's okay. So let's just back this out. 1 equals 3 minus 2. And from this equation, we know 2 equals 14 minus 4 times 3. So if we plug that in here, 1 equals 3 minus 4 times 3 is 5 times 3 minus 14. And so now we have 3 and 14. Let's replace the 3 with 17 minus 14. So 1 is equal to 5 times 17 minus 14, which is 5 times 17 minus 5 times 14 minus 14. 5 times 17 minus 6 times 14. And let's see if that works. So 5 times 17 minus 6 times 14 is 1. And 14 itself is 31 minus 17. So 1 is equal to 5 times 17 minus 6 times 31 minus 17, which is 5 times 17 minus 6 times 31 plus 6 times 17, which is 11 times 17 minus 6 times 31. So 11 times 17 minus 6 times 31, and that's equal to 1. So because this GCD was equal to 1, it's possible to write 1 as something times 31 plus something times 11, or 17. So that's Bezout's theorem. Okay, it says that this is always possible, and you can find the way to write your number as a linear combination by just working backwards through the Euclidean algorithm. I didn't give you homework questions on that. I should have, because it's actually kind of fun to work out. All right, so some other things about primes that I'll mention because they're good to know, and most of these will help us when we do crypto. So we're moving towards doing cryptography tomorrow and Friday. And Friday, hopefully, we'll talk about public key crypto systems. And we'll actually work through an example of how RSA works. And it's all built on top of modular exponentiation and all these facts about congruences and Bezout's theorem and things like that. And it kind of pulls it all together in this really miraculous way. So if P is a prime, and P divides A, B, C, D, E. All right, P divides a product of numbers. Then P divides A, or P divides B, or P divides C, or. In other words, if P divides a product of numbers, it must divide at least one of those numbers. That's only for primes, though. It doesn't work in general. For example, 6 divides 3 times 8, 24. But 6 does not divide 3, and 6 does not divide 8. So in general, this doesn't happen. But if 7 divides, I don't know, 4 times 7, 7 divides 7, right? If 7 divides 4 times 70, 7 divides 70. We can't have 7 divide A times B without 7 dividing at least one of either A or B. So that's one way we can sort of sneak up on some division with primes. All right, so here's another thing we're going to need to do crypto. So if A and B are relatively prime, so no common divisor other than 1, then there exists a unique x, and it's unique in the sense that we're working modulo something, so unique within that range of things that we want to deal with. So there exists a unique x such that a times x is congruent to 1 modulo m. Sorry, that doesn't make sense. If a and m are relatively prime. Then there's a unique x so that a times x is congruent to 1 modulo m. In particular, if m is a prime number and a is not 0, then there's a unique x such that a times x is congruent to 1. And someone observed this when we were doing those multiplication tables modulo numbers. When we looked modulo 5 or modulo 7, there was a 1 in every row, there was a 1 in every column. If there's a 1 in a row of a multiplication table, it means that there's something we can multiply a by that gives us 1. Right? So this is just a formal statement of that observation. And in particular, if there's a unique x such that ax equals 1, we can kind of write x equals the inverse of a, the thing you multiply a by that gives you 1. And this was another observation we had when we looked at those multiplication tables. We could define an inverse for all the numbers modulo p if p was prime. And so this tells us that if we have an equation, ax is congruent to b modulo m, and a and m are relatively prime, we can find an a inverse, and we could say a inverse times a times x is congruent to a inverse times b. And a inverse times a is just equal to 1, and so this is just x equals a inverse times b. So we can solve this equation for x in some cases, provided that a and m are relatively prime. So in the particular case where m is a prime number itself, we can always solve this equation, except when a is congruent to 0, because that's not relatively prime to p. So if we want to solve 3x is congruent to 2 modulo 7, there should be a solution to that. So what's the solution? I don't know. It's not 1, it's not 2, it looks like it's 3. Because 3 times 3 is 9, that's 2 more than a multiple of 7. So if we're working modulo a prime number, we can solve this equation in general. And that's going to be useful for us. Okay, one more result I want to leave you with, and I'm not going to prove this, but I'll just tell you that it exists, and we'll use this in public key crypto. This is called the Chinese remainder theorem. And this is actually referenced in some 1,000-year-old texts from China. So suppose we're told the following. X is congruent to 2 modulo 3. X is congruent to 3 modulo 5. And x is congruent to 2 modulo 7. Can we find a value x which satisfies all three of these equations simultaneously? And it turns out the answer is yes, provided that these moduli are pairwise relatively prime. So 3 and 5, 5 and 7, and 3 and 7 are all relatively prime. given that, we can always find a solution, x, to this system of equations. And I'm not going to go through that algorithm, but believe that there is a way to solve this. All right, so tomorrow I want to talk about Fermat's little theorem. That's a theorem from Fermat that is proven, so it's the other FLT, little instead of last. And that's the last piece we'll need to be able to do public key crypto. So we'll talk about Fermat's little theorem, we'll talk about homework questions if you have them, and then we'll start talking about crypto systems in general leading up to public key systems tomorrow or Friday. All right, I'll see you then.